Okay, so before the break, like we started looking at probabilistic generative models, right? Like, so where the idea is if you want to compute P of Ck given X, right? You can write this as P of X given Ck, P of Ck divided by P of X by using the base rule, right? Now, each of these terms here, they have a name. So P of Ck given X is called the posterior probability. Okay. P of Ck is called the prior probability. So what is the prior probability for seeing particular class? That is P of Ck. And like after you observe X, how does your probability change, right? So that is your posterior probability. And the P of X given Ck is called the class conditional density. And this is simply the density of X. Is that clear? Okay. So the first classification algorithm we are going to look at is called Gaussian discriminant analysis, or GDA. Okay. So GDA is going to make a couple of assumptions. Okay. So first, we're going to make this assumption that P of X given Ck, right, like the class conditional densities are Gaussians. Okay. And I'm also going to make another assumption to simplify the math, which is all classes are going to share the same covariance matrix. Okay. So I'm going to learn the prior probabilities and class conditional densities. Okay. The assumptions that I'm making are P of X given Ck is a Gaussian. I'm going to fit a Gaussian for the class conditional densities. And if you have 5 classes, you're going to have 5 class conditional densities, right? Like 5 Gaussians. So I'm going to make another assumption that all these 5 Gaussians share the covariance matrix, which means they only differ by their mean. The covariance matrix is same. Is that clear? Okay. So are these reasonable assumptions to make for a classification problem? Can I assume that P of X is a real vector, right? Like, so typically X is a bunch of features. Can I assume that P of X given Ck is Gaussian? So what does that mean? What does it imply? What are the limitations? Any thoughts? Well, first of all, Gaussian distribution is everywhere, right? Like, so it's one of the most common assumption that people make that the data is Gaussian, right? But what does that imply? Like, so it also implies that you're indirectly saying P of X given Ck is unimodal. Unimodal, like one mode, right? Like, so because a Gaussian looks like this, right? So you are kind of assuming that the data is in such a way that P of X given Ck is unimodal, okay? It is a strong assumption. The data need not be unimodal, right? However, it's okay. Like it's a decent assumption that we could make. We will see that it actually works in many data sets, okay? So it's not a bad assumption, okay? But what is too strong here is I'm saying that all the classes share the same covariance matrix. That kind of restricts the kind of decision boundaries that we could get. Okay, so we will see what kind of restriction it makes, like when we start looking at examples. Okay, but towards the end of this class, we will get rid of the second assumption. Okay, we're going to get rid of the second assumption today, but we might need to wait until next week to also get rid of the first assumption. Okay, so for now, these are the two assumptions that we're going to work with. And just as a quick recap, P of x given Ck, if I'm representing it as a Gaussian, then the density function for Gaussian is given by, now we are doing multidimensional Gaussian. Okay, so there are, let's say, d features. So then this is 1 by 2 pi power d by 2, 1 by the determinant square root, sorry, exp of minus 1 over 2 x minus mu k transpose sigma inverse x minus mu k, where the mean of the Gaussian is a vector mu k and the covariance is the matrix sigma, and this is just the determinant of sigma. Okay, yeah. Unit and exp. Yes. Yes. To the power of d by 2. Or d is the number of dimensions of this Gaussian, or the number of features for the problem. Is that clear? Okay, so this you should already know, right? Like a density function for a multidimensional Gaussian. So now let's go back, and I'm going to do the two-class problem. Okay, so in two-class problem, the probability of C1 given X is given by sigma of A, right? Where A is given by ln P of X given C1, P of C1 divided by P of X given C2, P of C2, right? So I'm going to simplify this now. So I can write A as, this is ln AB. So I can write this as ln A plus ln B, right? So I can write this as ln P of X given C1 by P of X given C2 plus ln P of C1 by P of C2. Right? So now I can substitute P of X given C1 and P of X given C2 with the Gaussians. Okay? So when I do that, you will have 1 over 2 pi and 1 over the determinant in both numerator and denominator. So they'll cancel, right? Like so those parts will cancel. You will just have the exp part, right? And even for the exp part, you're doing a ln. So the ln and exp will also cancel. Okay? So I can write this as ln exp of minus 1 over 2 x minus mu 1 transpose sigma inverse x minus mu 1 divided by, there is exp of the second Gaussian, right? I'm going to directly write this as minus times minus, so plus 1 over 2 x minus mu 2 transpose sigma inverse x minus mu 2 plus ln P of C1 by P of C2. Is that clear? So here the ln and exp will cancel each other. Okay. Okay, so we are going to further simplify this. So let me take this to the next slide. Okay, so this is my A, right? I'm going to further simplify this. So let me take the minus 1 by 2 out. Okay, so now I'm going to distribute the factors here. So this becomes x transpose sigma inverse x minus x transpose sigma inverse mu1 minus mu1 transpose sigma inverse x plus mu1 transpose sigma inverse mu1. Okay, then I'm going to do the same thing for this second term. The minus 1 by 2 is taken out, right? So you will flip the signs for everything. So minus x transpose sigma inverse x plus x transpose sigma inverse mu2 plus mu2 transpose sigma inverse x minus mu2 transpose sigma inverse mu1. Okay, the whole thing plus ln p of c1 by p of c2. Okay, now because I'm sharing the covariance matrices, right, you see that I can actually cancel the x square terms from the first Gaussian and second Gaussian. So x transpose sigma inverse x is same for both Gaussians, so I can cancel it, right? So then I'm just like I ended up with just linear terms in this thing, right? So I can write this as A is equal to x transpose sigma inverse mu1, okay, minus x transpose sigma inverse mu2 minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2. So I have brought in the minus 1 by 2 and did some simplifications. Okay, so plus ln p of c1 by p of c2. Okay, so if you don't follow this on the spot, it is okay. This is just simple algebra, right? Like, so I'm not doing anything fancy here. So you can go home and try to do it by yourself. You will get the same thing. Okay. So this is what we have, right? So now I can group things in such a way that any term that has x is separate and things that don't have x is separate. Okay, there are two terms with x here, right? So I can write this as x transpose sigma inverse mu1 minus mu2 minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln p of c1 by p of c2. Okay, so now I can write P of C1 given x as sigma of W transpose x plus W0, where W is given by sigma inverse mu1 minus mu2, and W0 is given by minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln P of C1 by P of C2. Okay, so what I have done is just grouping things together so that I can call this as W transpose X plus W0. It almost looks like the linear model equation followed by a sigmoid, right? However, the W and W0 are not directly the parameters. Like, so W and W0 are parameterized by the mu's, sigmas, and like P of C1 and P of C2. Is that clear? So I'm going to summarize what we did here. Okay, so the GDA model can be written as the probability of C1 given X is equal to sigma of W transpose X plus W0. This is how you're going to implement it. Okay, now here A, which is W transpose X plus W0, right? This is the A, has W and W0. W is represented as sigma inverse mu1 minus mu2. So we have to learn the sigma mu1 and mu2, right? Then W0 is given by minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln P of C1 by P of C2. Okay, Now, can you tell me what are the parameters of GDA? So what are all the parameters of GDA? What should we learn from data?
mu1, mu2, and sigma.
So mu1, mu2, sigma. Is there anything else?
PC1 and PC2 as well.
Yeah, we also need to know the priors. So we need to know the P of C1 and also P of C2. Is that clear? Okay. So we're going to see how to learn this. Okay. So before we do that, let's assume that we have somehow learned these parameters. Okay. So let us assume that we have learned these parameters and we can implement GDA. Okay. Now, what kind of decision boundaries we can learn with GDA, right? So this is a 0-1 problem, right? Like, which means when the probability of C1 given X is greater than 0.5, I'm going to call this class 1. When it is less than or equal to 0.5, I'm going to call it class 2, right? So the decision boundary is at 0.5. So I can write this as, oh, my decision boundary is P of C1 given X is equal to 0.5. This is my decision boundary. So this can be written as sigma of W transpose X plus W0 is equal to 0.5, right? Now I can bring the sigma to the other side. So this becomes W transpose X plus W0 is equal to sigma inverse of 0.5, right? So which is W transpose X plus W0 is equal to some constant. We don't care what that constant is. Now, all this is to say that the decision boundary for GDA is going to look like W transpose X plus W0 is equal to some constant. Now, what kind of decision boundary we are getting with GDA? Is it linear, nonlinear? Yeah? Everyone should say this quickly. So what kind of decision boundary are we getting with GDA? Yeah?
Linear.
It's linear, right? Like, it's just the equation of line. So we are only getting a linear decision boundary, even though the model looks nonlinear, right? Like, so the model is actually nonlinear, right? Like, so, like, if we go by the definition of linear model, a model is linear if it is linear with respect to the parameters. Look at the parameters of GDA. So the parameters of GDA are within sigmoid, which is a nonlinear function. So sigmoid looks something like this, okay? The sigmoid looks something like this. It's 1 by 1 plus e power minus a, right? We have a nonlinear model with just a linear decision boundary. So secretly, it's still a linear model. Okay, so these kind of models which look nonlinear, but their decision boundary is still linear, right? So we're going to call these models as generalized linear models. Okay, so they are still not very powerful. Like, so they are still linear models. Like, it looks like a nonlinear parameterization. Okay, so however, the decision boundary is still linear. Is that clear? Now, can you guess why we ended up with linear model based on the assumptions that we started with? Yeah? So can you guess why we ended up with a linear decision boundary based on that? Which assumption led to the linear decision boundary? Hmm? Yeah. The second one, right? Like, so here I'm sharing the covariance matrix, right? Because I share the covariance matrix, here you actually see that the x square terms actually got cancelled, which means if I did not share the covariance matrix, I would have ended up with a model whose decision boundary looks like x squared plus x plus something, right? Like, so which means it's going to be a quadratic decision boundary instead of a linear decision boundary, right? So that is another variant of GDA. Okay, so if you get rid of the second assumption in GDA, you're just going to get a more complex function, but it is also going to be richer in the sense it's going to give you some nonlinear decision boundary. Is that clear? Okay, so now for the moment, let's continue with having both the assumptions, which means like I'm going to assume that the class conditional densities are Gaussian, but also shared covariance matrix. Okay, now in that case, this is how the class conditional density would look like. Okay, so you see, this is P of x given C1. Okay, and this is P of x given C2. Because we made a Gaussian assumption, you see there is one mode for C1, one mode for C2, right? And here you see the probability of C1 given x. It looks like a sigmoid, okay? And there is actually a linear classification. Like, so the place where the sigmoid, like the place where the sigmoid jumps from 0.5, like, right, like above or below, like, so you have two different classes. So you will have a linear decision boundary. Is that clear? We still haven't learned how to learn the parameters yet, okay? So we're going to do that soon, yeah. Well, well, y is here, right? Like, so the decision boundary is linear because we are stopping at 0.5 below or above, right? Like, and that actually looks like a line in 2D and, well, in 1D and like a plane in high dimensions, or hyperplane in high dimensions. Is that clear? Okay, so now let's talk about how to learn the parameters, the learning part, right? Like, so how to learn the parameters of GDA. Okay, now to do a quick recap, the parameters of GDA are mu1, mu2, sigma, P of C1, and P of C2, right? So I'm going to assume that we have some training data, which is a bunch of xn and tn, for n is equal to 1 to capital N, okay? So we have capital N training data, okay? And we're going to assume that the Tn is going to be 1 for class C1, and it's going to be 0 for class C2. Sorry, what? Can you repeat what is T? This is just the data set. Okay. Now, I'm going to call the probability of C1 as pi, okay, which means the probability of C2 is just 1 minus pi. There are only two classes, right? The probability should add to 1. Okay. Now I can write the joint distribution P of xn comma C1 as basically probability of C1 multiplied by probability of xn given C1. Just a chain rule, right? So this is pi times the density, the class conditional density given mu1 and sigma. Similarly, P of xn comma C2 is given by P of C2, P of xn given C2, which is 1 minus pi times the Gaussian. Here the Gaussian is conditioned on mu2 and sigma. Is that clear? Okay, so now let's take this to the next line. Okay, so typically we need some loss function to minimize, right? Like, so if you want to learn the parameters, you want to construct some loss function and you want to minimize this loss, right? But now we have probabilistic models here, right? So we are talking about probability of C1 given X or probability of C2 given X, and we're also talking about the joint distribution, right? So what we are going to do here is slightly different than what we did before. So instead of minimizing some loss function, okay, I'm just going to maximize the probability of the data set. Is that clear? Because we have a probabilistic model and we are trying to approximate the functions using Gaussians, right? Like, so I want to find an approximate probability distribution that will assign very high probability or the maximum possible probability for the data set that I have. Does it make sense? So now we are going to talk about likelihood of seeing a particular example. Okay, let's take some example xntn. Okay, this is an example, right? Now, what is the likelihood of seeing this example? Okay, what is the likelihood of seeing this example? I think it depends on what is Tn, right? Like, so if Tn is 1, the likelihood is given by P of C1, P of x given C1, right? If Tn is 0, well, depends on what is 0 and 1. Like, for one class, it is P of x, P of C1, P of x given C1. For the other class, it is P of C2, P of x given C2. So I can write it in a compact notation. So I can write this as the likelihood is basically pi times n of xn given mu1 sigma, okay, for class Tn, and 1 minus pi times xn given mu2 sigma for 1 minus Tn. Yeah. Target. Yeah. Okay. I'm using Tn instead of Yn to differentiate regression and classification problem. Okay. So what does this mean? This means that when Tn is 0, we know that it is class 1, right? So which means the second term becomes 0, like 1, right? Like, so you just have this first term, which is pi times the first class conditional density. When Tn is 0, this term disappears, but you have this term, which is 1 minus pi times the second class conditional density. Is that clear? So this is for one example, right? Now I want to compute the likelihood for all the examples in my data set, and I want to jointly maximize the likelihood for all the examples in my data set. So which means I should take a product of likelihood of all the examples in the data set and maximize this product, okay? So the probability of the entire data set, okay, the given pi mu1, mu2 sigma is simply product of n is equal to 1 to capital N, okay, pi n x n given mu1 sigma power Tn, 1 minus pi n of xn given mu2 sigma the whole power 1 minus Tn. Is that clear? So this is called the likelihood function. Okay, and I'm going to set up a mathematical objective to maximize this likelihood function. Okay, just like how we do least squares for regression, for classification, we're going to do maximum likelihood approach. Okay, like I want to maximize the likelihood of seeing the entire data set. Yeah. Yes, I want to find pi, mu1, mu2, and sigma that maximizes this likelihood function, the data set. Yeah. Okay. So how do you find the maximum of a function? You derive it and set it similar to minimum, right? Like you can derive it and set it to 0. And if you want to do an iterative approach, instead of doing gradient descent, you can do gradient ascent. Okay, because you want to find the maximum likelihood. Is that clear? Okay. So this is a really important thing that you should internalize. So I'm going to repeat what I said, but with a simple example. Okay. So in classification, typically you're given with some data set. Okay. Let's say I have a data set which has x1 t1, x2 t2, x3 t3. Okay. This is my data set. Okay. And you also have some model with parameters theta. Okay. So the likelihood P of d given theta is defined as the product of I is equal to 1 to capital N, the probability of xi comma ti. So that is the definition of likelihood. Okay. So now I can apply chain rule and say, oh, this is product of I is equal to 1 to capital N, P of ti times P of xi given ti. Is that clear? Okay. So here I'm implicitly making a couple of assumptions. Okay. The first assumption that I'm making is all the examples are identically distributed. Okay. This is an implicit assumption here. I'm assuming that all the examples actually come from the same distribution. Right. So that is when I can use the same form for the density function, right? Like I'm assuming that all the examples come from the same distribution, okay, which is the original distribution. And I'm also making this assumption that all the examples, right, are independent. Okay, that is when you can do this product of 1 to n individual probabilities. I'm assuming that these examples are independent. So the other way to say this is like, oh, this data set is sampled from the true distribution, and the order of sampling doesn't matter. Like I can just shuffle the data. Shuffling is not going to change the solution. Is that clear? So this assumption, right? These two assumptions, like together, we are going to call this as IID assumption. Okay. So which just means that I'm assuming that the data is independent and identically distributed. Okay. So this is one of the most common assumption that almost all the machine learning algorithms we're going to see in this course is going to make. Okay. So this means that somebody is giving me a data set, and this data set is sampled from the same distribution. The order of distribution doesn't matter, right? This makes it easier for me to learn a model, like which is basically some approximation for this distribution. Is that clear? Any question? Okay, so now let's go back to the likelihood function, right? copy this. Okay. So this likelihood function you see is a product of probabilities, right? Typically, you're going to have lots of examples, like which means let's say you have 10,000 examples in your training set. Then this is basically product of 10,000 probabilities. So as you can imagine, we cannot implement this in computers, like so due to numerical precisions and limitations, like so you're going to get into overflow or underflow errors, right? Like so you cannot multiply 10,000 values that are between 0 to 1. Okay, so what we will typically do is to convert this product to summation, we will consider the log probability instead of the probability. Okay, so the ln p of d given pi mu1 mu2 sigma. Okay, which is basically summation I is n is equal to 1 to capital N. Okay, ln of pi n1 power tn 1 minus pi n2 power 1 minus tn. Right, I'm just writing n1 and n2 as shortcuts, short forms. Okay, so this I can write as summation n is equal to 1 to capital N tn times ln pi n of xn given mu1 sigma, okay, plus 1 minus tn times, okay, sorry, ln 1 minus pi n of xn given mu2 sigma. Okay, so this function is called log likelihood function, and the way in which we are going to learn our parameters is called maximum log likelihood criteria. Just like how we do least squares for regression, like we will do maximum log likelihood for classification. Yeah. So T of n is? Oh, no, times. So that's a ln. Just a, is that clear? So now we have the objective function, right? So the objective function is just to maximize this log likelihood. So which means I can differentiate this function with respect to pi. I'm going to get the answer for like whatever the optimal value for pi, like the parameter, right? I'm going to differentiate this with respect to mu1 and set it to 0. Then you'll get the value for mu1. Do it for mu2, do it for sigma. You get all the parameters. So then you can go back to the GDA equation and implement it. Is that clear? Okay, so let's take a 10-minute break.